Hello, everyone, and welcome to our Fellows Public Talk. I'm Claudia Rizzini, the Executive Director of the Radcliffe Fellowship Program at Harvard University. Before I introduce the speaker today, I would like to encourage everyone to ask questions. We will address them at the end of the talk. You can do so, you can ask questions by using the Slido link, which is posted here on the side of the room for our people in the room with me, and in the chat feature of the Zoom webinar for our online audience. Thank you. It is my pleasure to introduce today's speaker, Erin Treacy Solovey. There has been a staggering amount of reporting and media hype in the last year about the future of human-computer interaction in our daily lives, what it means for education, for our jobs, and our basic day-to-day tasks. And much of that has focused on the capabilities of AI, or artificial intelligence, to mesh seamlessly in our routines. But computer scientists like Erin would argue that AI can only become an integral part of our lives and our work if it's usable. And to be usable, such tools need to be designed around our fluid cognitive states. AI-based systems in cars need to be built around humans thinking while driving cars, not how they think while watching football. Erin's work, which sits at the intersection of human-computer interaction and neuroscience, seeks to augment human abilities through adaptable intelligent systems. From how we learn in school to how we drive and much in between, Erin have used brainwave data to inform her research and optimizing task performance and human-computer collaboration. While at Radcliffe, she is continuing to leverage advancements in brain-computer interfaces to explore possibilities for real-world intelligent systems that adapt to changing human cognitive states in real time. The Q&A portion of the public talk today will be moderated by Jody Snyder, Associate Professor of Information Science at University of Illinois, Urbana-Champaign, and Perrine Moorhead-Grayson and Bronze Grayson Fellow at the Radcliffe Institute. And now please join me in welcoming Erin Treacy Solovey.
Hello, everyone. Thank you, Claudia, for that wonderful introduction. I know we have a lot on our minds today, and I really appreciate all of you being here today. I'm really excited to be here and to be part of this community that we have at the Radcliffe Institute. It's been so amazing to hear about all the projects happening across so many disciplines and participating in the discussions around that. So now I'm really looking forward to talking to you about my research, which is in an area of computer science at the intersection of human-computer interaction, artificial intelligence, and neuroscience. And I also welcome all of your perspectives that you're going to bring to this, because AI is really advancing rapidly, and its impact on people on the planet is substantial, and it's growing. And so I'm looking forward to our discussions. Okay, so here we go. So let's talk about the brain. So we're in a really exciting time right now. Advances in research in brain science and new technology for monitoring the brain is really changing what we know about the brain. We're learning so much. And this is coming from a lot of investment from, for example, the US government and the US Brain Initiative, which put a lot of support to research, including my own research with the US Brain Initiative, as well as what we're seeing in the commercial sector, where a lot of companies are starting to build new technologies that take advantage and allow us to really monitor brain activity in different contexts. And so this is really opening up a lot of research opportunities. So at the same time, we're, as we know, seeing a lot of advances in sophisticated artificial intelligence. And whether it's robotic surgery or advances in transportation, like cars, diagnosis of medical conditions and things like that, as well as education. So a lot of the reasons that we're integrating AI into these human-computer systems is we have this goal of having improved effectiveness of these systems. And so to achieve those benefits, the system and the user really need to have awareness of what they're each capable of. So what are the strengths of the human? What are the strengths of the AI system? And this is really important, and it's not always the case that we have that understanding. And in fact, that's where a lot of the breakdowns happen when we have issues. So we see bottlenecks in systems due to human perceptual limitations that we might have, as well as the AI's limited ability to tell and detect what is the full spectrum of the user state at the moment. So we have these failures because we don't understand or consider what are the strengths and the weaknesses of the human and the machine. And so here I put up just some. This is not a comprehensive list, but we really do need to understand what are the strengths of humans, what are the strengths of AI, and how we make them work. So I've listed some. For example, we all know computers can process massive amounts of information. It doesn't get bored or tired. A robot can repeat the same thing over and over and over again. A human, on the other hand, if you ask them to do things 24/7, all day long, repeatedly, they're probably going to have some performance breakdowns. But on the other hand, humans are really good at adapting to new information and new situations, even on limited data. Whereas AI, we tend to think of needs big amounts of data in order to make the right decisions. And so when these work together, we can have a lot of effective interaction. So a lot of what we do in human-computer interaction is think of this intersection. How do we make it more effective? And sometimes this involves really understanding the human and what they're capable of at a particular time. Sometimes it's really digging into machine learning and building better models and things like that. And sometimes it's that interface. And so a lot of the work that I do is looking at how do we come up with new interfaces. Like you can think of the mouse and the keyboard as user interfaces, but what are other types of interfaces? And so in this talk, I'm going to go into some of the work that I've been doing where we can look directly at the brain and use information that's coming as a way to create these better synergies between the human and the AI system. But first, I'm also going to step back and talk a little bit more about human-computer interaction in general. So why do we build these user interfaces? This isn't a new field. So even though AI seems like it had rapid advancement overnight a couple years ago, it's actually been going on for a long time. So computers have been advancing and gaining power and can process massive amounts of information. But over the same amount of time, humans really, in the last 50 years, our own capabilities have not changed really at all. We still have the same senses and things like that. And so we try to make people more effective by looking at user interfaces. And so if we look over time, early systems, this is actually a machine at Harvard that was built at Harvard. This picture is from 1944. So early systems, the way that humans gave information or commands to computers was really complicated on these pieces of tape that got punched or these punch cards. And so you could, at that time, most of the human-computer interaction was figuring out ways to take a computer that can do something really well, like one particular thing, computing, but it's actually a limited resource, and so there's a lot of work, and in fact, sometimes there were whole rooms of people creating programs in order to make the computer do something. And so it was a lot of work on the human side. Later on, as computers advanced, we moved into command line interfaces. There's been a few other things, but command line interfaces were kind of a new generation that made interacting with computers and telling them what to do look a little bit closer to how people already understand things. So it used words and numbers and things that we're already familiar with. And today we still see some of these as well, like if you use Unix or anything like that, it's still a command line interface. So these are still around. But then, if we look today at most of our user interfaces, we see graphical user interfaces. And this is using the mouse, the keyboard, things like that, and clicking on things. And so when we had these advances in when graphical user interfaces came out, this really changed computing. So this is where we start seeing personal computing. We saw it not just being experts using computers. And so it opened it up to a lot of new people as well as new uses of computers. And so as computers are getting more powerful, the user interfaces are also evolving and changing who has access to computing and what we use computers for. So again, if we look at the user interfaces today, a lot of the stuff that we're doing was based on research in the 1960s. So Ivan Sutherland's Sketchpad system in 1963 planted the seed for a lot of the graphical user interfaces that we use today. And then in 1968, the mother of all demos, which was Douglas Engelbart's demonstration of many different new technologies, but what it's most remembered for is it was the first introduction of the computer mouse, and so that's what it's kind of holding a prototype in his hand. And so, of course, these were very early prototypes, and then it took years and years of refinement to get where we are today, and polishing and things like that. In other areas like mobile device or touchscreens, we also saw them being researched in research labs many years before we started seeing them in our pockets. and so, of course, in that process of refinement, we've also taken some wrong turns. So as long as there's been user interfaces, there's been bad user interfaces. And so we have error messages that don't necessarily make sense or aren't very helpful. We have assistants that try to be helpful, but sometimes are more annoying. And then there's also situations where the user interfaces problems have actually been deadly. And so these are a couple of examples of when excessive radiation doses were given to patients. And of course, we've heard about some of the crashes that have happened in autonomous driving situations. So the field of human-computer interaction is continuing to learn from mistakes and evolve its methodologies to enable effective development of useful interactive systems as the technology platforms that we're using change. And so if we go back to this, if we think of the seeds of graphical user interfaces being planted more than 50 years ago, I'd like you to really think for a minute, where do you see computing in another 50 years from today? And what would you like it to look like? And what needs to be done in research labs today to pave the way for these future innovations? And how can neurotechnology help? Okay. So there's a lot of interesting interaction techniques being developed in research labs today. And they're making their way into commercial products as well. So, we have voice. Some of this stuff was in research labs, and now we can talk to Siri and things like that. And in my research, I've touched on a lot of these and thought about how they're designed and what we can make possible with them. And so I'm going to focus or get to work on brain-computer interfaces, but I am also going to touch on some of these as well, because the work that's happening in brain-computer interfaces is happening at the same time as all of these advancements are happening. And all of the stuff that's on the horizon are kind of converging. And so I keep in mind a lot of these advancements while I'm working on it. One thing to keep in mind when I'm showing some of this research is that a lot of the work in labs, including my own, are proof of concept ideas and concepts that are similar to when the Sketchpad and the mouse were just kind of demonstrated, but we didn't know all of the potential. So some of these are, very early stage. And I'll just touch on a few because I think it's good to connect with some people who might be interested in some of these. So some of the work has looked at things like AI agents that are more embodied than just the chat bots. And so how do you design them so that people can work effectively with them? But also, how does the design of these agents impact their interaction? And so we did some studies looking at how an agent's behavior changes how you perceive the agent and how you perform with the agent, as well as how you're going to interact with future agents. And so some of our findings were expected. If you have a cooperative agent, your performance on a task is going to be better. And also, you're going to trust a cooperative agent. But the interaction, there's a bunch of different things. I've just highlighted a couple of them here. But participants who interacted with an uncooperative agent actually had higher trust for the cooperative agent that they then worked with than someone who always was working with cooperative agents. So that's one thing to keep in mind, that in a previous experience with AI or a system is going to impact how you perceive future ones. And also, sometimes people do have a tendency to overtrust a system. So even if they have made a decision, they know what the right thing to do, but the agent tells them to do something different, sometimes they just do it because it's easier, or they're like, okay, I'll just try it. And so this changes our behavior and our performance, and so these are things to keep in mind. And then I'll talk about a few different things of just different ways of interacting. I had done, a long time ago, I was doing work on tangible interfaces, and I'm showing this because it was an idea, it was working with physical objects instead of digital pixels in order to interact with a computer, and we had a project with Michael Horn, who's professor at Northwestern, and we were working with this tangible programming language that he developed and made an exhibit at the Science Museum here in Boston. And what we saw when we changed from using a graphical user interface for the exhibit to teach about program to tangible form, it really changed how children and families interacted with it. And so again, this is where when you develop new interaction modes, it changes who's using them and how they use them and what you can use them for. And so we found it was much more intrinsically motivating for children and encouraged active participation. A couple more things. We're also working on projects looking at these smart fabrics that have they have conductive thread in them, and because of that, you can detect where someone is touching on it. And so this could be used on clothing, it could be used on furniture. And so what we've been looking at is first stuff related to more algorithms of how do we detect exactly where someone is touching. But then from that, what we were really trying to do is if we combine it with things like augmented reality, where we can project things onto it, and so these are early prototypes, our goal was thinking really about in-person co-located experiences and how we can foster kind of communication between parents and children about feelings. And so that's what we had, this cozy blanket that they could talk about their feelings, and that's what's in that picture. This was something some of my undergraduate students developed. They were inspired by quilts and memory quilts, where they could store their memories of their college experience in the quilt, in the fabric, and have fabric representation, but also if they had the augmented reality, you could kind of see memories and photos and listen to music. So anyway, these are just different things. And then one more example of some of the emerging things that we're developing is we also created this system where you could use mini gestures that you write letters on your finger. And based on that gesture, we can detect that gesture. And so you could detect the whole alphabet just by writing, if you write A, B, C on your finger. And the way that we were doing this was using these miniature radar sensors that are getting embedded into different products like phones. And so we were just trying to explore how could we build a classifier. So this is a machine learning classifier just showing what letter we're predicting the person's doing. And then imagining how this might be used after we built the machine learning work. And so here are some examples of where you could use it as input into your computer. You could type, although you could just type with a keyboard too. But we were also thinking of other places. So maybe you can just privately be entering input into your phone silently, without maybe indiscreetly. And then the other example is for your watch. So instead of having to tap on things, and you could actually give text input into your watch. And so these are some of the examples, but the idea is having a touch-free, private, familiar text input. So these are all just some explorations we've been doing, and they're cool and interesting or emerging. Some of these emerging technologies are coming out, but they don't fully capture the richness of your thoughts and intentions and feelings when interacting with technology. So, for example, when we communicate with other people, we not only say the words, but also we have gestures, eye contact, and other signals that we're giving off to the other person who may or may not adapt their behavior, but they could detect some of that. There's also just automatically these other things happening, like a physiological response is happening, which the other person may or may not know, but it's just something that naturally happens. And so when we communicate with computers, we also might generate there might be other things going on, and we might generate these signals, but the computer currently has no way to detect them, and so it completely ignores them, and it's not going to change its behavior. And so a lot of the work that I'm doing is seeing if we can detect signals that people are giving off in real time and incorporate them into the user interface to improve this communication channel between the computer and the human user without too much extra effort required of the user. And so if we can do this, then we can improve the communication and make systems that are more supportive of the user's changing cognitive state. And this is increasingly valuable. As I was talking about, computers are becoming more and more popular, more and more powerful and pervasive, but our cognitive abilities really are not changing considerably. So in human-computer interaction, there's already been a lot of work where whenever people are interacting with technology, we are trying to figure out what's going on, what is their cognitive state. And so there are other methods besides brain sensing. And so you could just observe people, you could ask them questions, you could every once in a while send them a message to respond to and ask them if they're distracted or something like that. You can also look at things just from their behavior at a computer, so how long does it take them to do a task, things like that. We can have sensors in the environment, use computer vision, and then physiological measures. So these are all really useful to human-computer interaction researchers because we really want to understand, when we give someone a task and we give them this interface, is it doing what we want it to do? So of course, I'm focusing now on what we can do by looking directly at the brain. So if we could look at brain data and in real time, what will that tell us? So in human-computer interaction, this has been kind of a building, increasing research area and part of that is due to the fact that technology is becoming less expensive and more realistic and practical for real-world settings. So a lot of the work that I was doing in my early work was just showing the feasibility. Can we actually detect what's going on in your brain in the real world? And so these are some of the sensors we've used. There's EEG and FNIRS, which I'm going to talk about both of them a little bit more, but also other physiological sensors like heart rate, skin conductance. These all can pick up these signals that are happening to all of us all the time. And so if we can detect them, then you can take what's going on in the user's current state, give that information to the system or the AI agent, and then it can adapt to their current state. And so this is an area where there's a lot of opportunities these days because of the technology that's emerging. But what I'm talking about in my use of brain sensing is actually very different from a lot of the work that had been done for a long time in brain-computer interface research. So much of the early work on brain-computer interfaces was mostly for patients who had no other way of interacting. So they might be paralyzed or they might be locked in. And so people were developing ways that you could use your brain waves in order to directly type things by trying to select letters or by things like imagining your hand moving, and then your left hand, and that could turn your wheelchair a certain way. And so these were really amazing interfaces that picked up brain data, did some signal processing, and turned it into a control signal that enabled people who had no other way of communicating to communicate. And so, the thing about those, let's go back. Is that it really required a lot of concentration and training in order to do this. So you have to, and you can't do anything else at the same time. You're putting all your effort into thinking about creating this brain state, and then use it to control something. And so while it is super valuable if you don't have other ways of controlling your computer, for people who are able to type with their keyboard, it's much easier to just write an email by typing than to write an email by thinking with your brain. And so I'm not doing work in that area when I'm thinking about work for this wider population. And so this is sort of that model where there's the human, they think something, you pick up the signal from their brain, and that gets sent to the computer, but that's the only input going into the computer. Instead, much of the stuff that I'm doing is using some other input device also, and then the brain data is just a supplement to it, and so we're picking up what's happening just naturally instead of focusing so much on it. And so we talk about this as a passive input channel, an implicit input channel, and it's passive because you're not focusing all your attention on controlling your brain waves, we're just passively picking up what's happening. And it's implicit because then you're giving these implicit commands, similar to, let's say, if you walk into a room and the lights turn on. That's you didn't flip the light switch, but it implicitly figured out the light should go on right now. So that's where my work has been. And so when we think of the brain as this implicit supplementary input, we can think about augmenting other devices, targeting a wider audience and group of users beyond just people who are disabled, and think of it as capturing these subtle cognitive state changes that are happening and using it as input. So to make this a little bit more concrete, I'll give an example from one of my students. So as a proof of concept, one of my students worked on a game, and the game adapted to your brain data. So you were walking through an environment, and the idea is, when you're really focused on something, you can take it all in, and then when you're distracted or thinking about something else, it might feel a little bit more foggy, like this. And so we created this game where someone's walking. And so they're using, and this can be in VR, so you're walking around, or it can be on a computer. And there's multimodal sounds and visuals that you get. And meanwhile, you're wearing the brain sensor. And when it detects that your brain activity is low, it changes the game behavior, but not the walking. So it's not changing your primary task of walking, it's changing the peripheral stuff. So things get a little bit foggy. And then when their brain activity is high, then things become clear again. And so this is just a proof of concept of showing what this could look like. And so to do this, we need to look at the ways that we can measure brain activity. And so most brain sensing technology was not developed to make video games. It was really for clinical purposes. And so we see these big machines, very expensive, like MRI, PET scan, MEG. And these have been some of the tools that have allowed us to learn a lot about the brain. And that's great. But they're not practical for real-world use. And so what we started to see is EEG systems and FNIRS, functional near-infrared spectroscopy, which I will talk about, start to emerge. And these have characteristics that make them more practical for real-world settings. So you can't bring a computer into an MRI. It's a humongous magnet, whereas you can look at the brain at a computer and using these other tools. And so this really was exciting as a human-computer interaction researcher because we can look directly at the brain while people are doing more realistic tasks. So functional near-infrared spectroscopy, or FNIRS, which is how I'll probably refer to it, it is not usually that familiar to people. So FNIRS uses light, and near-infrared light, in fact, and it sends light into, so there's every setup, whether it's a headband or a cap, has light sources and light detectors. And so the light sources send light into your brain and into your head, and your bone and tissue is transparent to light at these wavelengths. But the oxygenated blood is what absorbs most of the light. So it's actually very similar to a pulse oximeter, but for your brain. And so it's picking up blood oxygen levels, basically, in the brain, and it's becoming more practical for research. So yes, these are light sources. The light goes through tissue and bone, and then because of whatever amount is detected that comes out, we know that the main thing that absorbed it is the oxygenated blood, and so we can calculate how much is there, and that's a measure of brain activity. So EEG, which you may be more familiar with, is different. It's looking at electrical activity that comes to the scalp. Again, from the same source, it's still brain activity that's creating it, and so it's just a different thing. And so you can also use EEG and FNIRS together. And just so that you have some sense of what this looks like, it's really, if you just take the data, it kind of looks like this, or something along those lines, and it's just lots of time series data that we have to make sense of. And I could give a whole talk on signal processing and machine learning, but I'm gonna keep this short. But in order to build brain-computer interfaces, we always have to go through all of these stages and think about all of these things. So the user performs a task that generates brain activity. And then from that brain activity, if we have sensors, we can detect them and get that raw signal that I was showing, do some pre-processing and getting rid of noise and things like that, and then build a classifier and do this online machine learning that can detect, oh, okay, this person is getting stressed right now, or this person is falling asleep right now. And so we can do that. And then the important part for human-computer interaction research is, okay, if we build this really good classifier, what do we do next? How do we interpret the cognitive state information given the tasks that they're doing? And how do we adapt the interface? So we really need to be doing all of this in order to, all of these steps go together. And so in my lab, some people are really focused on machine learning algorithms, some people are more focused on the user interface, and sometimes the whole picture. And so I'll give a few more examples to make this more concrete of how, I said that this is a different type of brain-computer interface than those traditional ones where you focus all your attention on controlling your brain waves. And so I had done a lot of work looking at people when they're driving and trying to use this, not so much necessarily right now to adapt so I do not advocate using your brain waves to drive a car. This was more to see if we can detect when you're driving a car and doing another task, can we detect that you're actually, it's a different cognitive state that you're in than when you're just driving and staying focused. Because a lot of people think that they can do multiple things while driving. And so we were able to look at brain and physiological responses to see what happens in the car. And other situations that we've looked at are people supervising multiple, like either a really complex situation, multiple vehicles or drones, and making really complex time-sensitive decisions. And so we're really using the brain data in real time to figure out when someone's experiencing high workload or low workload. And so what I want to talk about here is if we can detect workload, an important thing for human-computer interaction researchers is to understand that we know that if you look at workload from low to high and performance from poor to good, when we have really low workload, humans tend to start to get bored, not pay attention, fall asleep. And so the performance can be poor there, and we all know that when we have excessive workload, then we start to make mistakes because we're just overwhelmed. And so if we were moving more into a brain adaptive system, we could have systems that kind of are keeping track of, is someone starting to just zone out because there's not enough to do, or are they experiencing extremely high workload, and then you could adapt the task that they're doing or adapt the level of autonomy or AI, where does the AI get engaged? If they notice that people are experiencing very high workload, maybe it can help more. But if they're helping too much, then the person starts to get disengaged and not pay attention to what's going on because they're relying on the AI. And so we can adapt the autonomy level. In games, we can change the difficulty of the game. As we all know, if it's too easy, we don't want to play the game. It has to be just that right level of challenge. We could also do things like modify how much information we present to someone at a given moment based on what we think they can perceive right then. Or we can transform the modality of information. So maybe we need to give auditory alerts in addition to the visual indicator because they're overloaded. And then things like managing task allocation and difficulty. And then the other thing is just, that's all for real time, but the other use of it is really just putting this on while people are doing tasks and looking later to see, were there moments that the person was overloaded that we could then redesign the system to avoid that in the future. Okay, so go into a few other projects in the same idea. So we have a grant from NSF where we're looking at people while they're learning and students while they're learning, particularly focused on math. And the idea here is not so much that I imagine classrooms where everyone's wearing brain sensors, but it's more, could we start to understand the learning process in the real world as opposed to in these really controlled experiments. And so and then be able to come up with better and more adaptive learning teaching techniques. So what we're doing a lot of studies looking at the level to which we can detect things like going from a novice to an expert, and do we see changes in the brain, as well as some of the metacognitive states that happen when you're learning. So things like mind wandering and focus and staying on your goal, and use those and figure out if we can detect them, and then what types of interventions are effective when you notice those particular states in the student. And so then when we do that, we can make these, there's already a lot of work on intelligent tutoring systems which do not use brain data. They just look at how long it takes a student to answer a question, how many hints they need, and they build a whole model of like, how is the student learning, and how can we help them, how can we provide better learning content. But it's all based on key presses and pause, how long something takes, which is really a pause in using your computer. So you might see a problem, and then it takes you a while to answer it. And so a lot of the research there in this educational data mining is looking at what does it mean if someone sees a problem and pauses for a long time or a short time? Are they deeply reflecting on the material, or are they mind wandering? And so what we're thinking, and I'm collaborating with people in the learning sciences, is that if we can fill in those gaps by actually looking at, in those moments, what's going on, are they mind wandering or are they deeply reflecting, then we can have the correct assistance to them. And so we're building on a lot of that work. And that's ongoing while I'm here. And then another project that I'm working on is looking at people working in teams. And so we're not just putting brain sensors on one person, but we're putting them on everyone working on the team and seeing if that tells us anything about teamwork and when we're having effective teamwork. And so this gets back to what I was talking about, where humans can adjust to what they see in another person and maybe change their behavior. But there are also times when people don't notice things and don't adjust, and maybe the team is missing something. And as we work on distributed teams where we might not be co-located, we're starting to lose some of that. And so the study that we're currently running is looking at people where some people are in one place, some people are in another place, they're working together, and of course, they're also working with AI system to assist them. And so we're looking at when do they engage the AI, when is it useful, what can we tell about individual metrics from the brain, so is this person experiencing high workload or stress, as well as joint measures of team dynamics. And so, and there's some research showing that in some cases, people's brain activity and physiological responses can synchronize. We're looking at some of those things too, and whether it happens or whether it doesn't happen in these contexts. Yeah, so these are just more examples of stuff that's more done. So we did show that if we look at people's brain activity and adapt the way tasks are allocated, so this was in a really complicated kind of supervision of UAVs that have to move in certain ways. And we saw that we could reduce errors, and we could, by just allocating, when we notice a particular state that someone's in, kind of moving it off of their workload level, off of their task, so that they can focus on the most important things. And we saw a reduction in errors and things like that. And then this is just showing some of the data from the driving. So I did a brain sensing experiment in a lab setting, which I showed before. And then I also did one on the road where we weren't looking at brain data, but we were looking at physiological responses. And this was giving people a driving task as well as a secondary cognitive task that they had to do while driving, to kind of get the feeling of, if you're also paying attention to your GPS or if you're doing other things in the car. And we saw, won't go into all of it, but we were definitely seeing, when you see these different bands of color, that was when they were just driving versus when they were driving plus doing a cognitive task at the same time. And another important thing that I was talking about, we have also studied very low levels of workload and what happens. And in order to do that, we had to do these boredom studies where we basically have people do something for 3 hours, where they're in the room for 3 hours, but we basically ask them to do something once or twice in that time. So most of the time, they're just sitting there waiting. And so we could really study, and we were able to pick up some of the some of the things that happen when you transition from being in this state of very low workload for a very long time, and then all of a sudden you're asked to do something. What happens? And we see things in the brain, and we saw differences in people when they were either able to do it very well in transition and other people who were not. And so we're looking to build on that and see how we can support that, because this happens in a lot of cases, and it's going to happen more and more as we rely on autonomy more and more. So for example, if you're flying a plane and it's mostly on autopilot and then something happens, how do you re-engage? Or, and there's other situations too. Okay, so yeah. So those are some of the examples of things I've been working on. And the goal is to really think about, and it's also, there's other people working on similar things, and using the brain data to enhance human-AI interaction. And so these are some of the goals and hopes that I have for human-AI interaction with brain sensing, that we can use it to prevent errors, to improve communication, improve our performance, our memory, our mobility, make better decisions, accelerate how we learn, and entertain us, make better games, and just overall make us happier and healthier, because we can also start to look at things like sensing your brain and your physiology in the real world. Even just, if you happen to be stressed on a particular day, you might be able to start monitoring that in the real world passively. So there's a lot of promise. I would also say that inevitably, anytime I hear mention of brain-computer interfaces in a book or a movie or a TV show, it always has pretty frightening consequences. So things like surveillance or brain control, deception, and just basically all kinds of unintended consequences. So this is from Black Mirror, if you haven't seen. And so brain implants are a big topic in the series in Black Mirror. So I realize that there's a lot of concerns, and we really can and should learn from fiction, because these are things that we need to start anticipating as we move into the space. And I'm very interested in that part of it too. But I would say we're still, with brain-computer interfaces, we're still kind of back here, like where graphical user interfaces were. And that's fine. It means that there's a lot of work to do, both on the technology development, models, machine learning, but also on the user interfaces and the decisions about how and where we use it. And so we have a lot of work to do in order to get it right. And I think the field of human-computer interaction has really, that's what we do. We really look at both how can we build technology that enables new things, but then how do we study it once we build it and see how people use it. And that's what I'm really interested in. So I've always the reason I got interested in this field is because I really like computer science and things like that, but I also like people. And so I'm excited about a lot of the work that's going on at this convergence of human-computer interaction, AI, and neuroscience. And I'm really passionate about improving the way that humans interact with technology, and both in this human-computer interaction or also human-AI interaction, because AI is developing so fast and so powerful. So there's a lot of really amazing things that we could do with AI as well. But we have to, and it could solve a lot of our problems, which we know we have a lot of problems right now. But it has to work for people and solve real needs. So that's where I'll leave it. And so I want to acknowledge, a lot of this couldn't have been done without my students, and so a lot of students have worked on these projects and collaborators. And so I've really enjoyed having the opportunity to share this with you, and I look forward to having conversations about how to apply some of this into new areas and new domains, and I'm happy to have more questions. Thank you.
Erin, what a wonderful talk. I'm so delighted to get to have this conversation with you. So I wonder, the science fiction always comes to mind, partly because I love reading science fiction, and partly because you mentioned in your talk kind of openness to other perspectives. And I know among our fellows, we have some artists of many sorts, including novelists and filmmakers and so on. do you think that it would help to communicate the potential of brain-computer interfaces in a less scary way? Are there things that you're excited about that you think, well, no, that can't be used in a harmful way? Or it would just be like, are there positive versions that you would envision that people could push forward?
So of brain-computer interfaces?
Or just brain-computer interfaces, or the wider space that you're working in?
I mean, so are there not scary? The question is there not scary? I mean, yeah. So I think that there's a lot of potential, and a lot of people are, I have my hesitations, but a lot of people are really excited about some of the things that we can do by, avoiding some of the catastrophic errors and mistakes that people make because they're overloaded or underloaded. I also see a lot of potential in being able to monitor your state throughout the day, and for your own personal understanding of how your, how your brain is working, how you're are you stressed right now? How do you connect what you were doing at a particular time and how your brain started to be stressed and things like that. So I think that and then of course, there's a lot of stuff with games and just overall human performance just being more optimized, and collaboration. But I think, and then the other thing is just being able to assess how some of the things that we work with in technology, some of the things we do at work, or some of the things what is causing us stress and how can we mitigate that? So we can use it to understand when things are not working in our brain and try to fix those problems. But yes, I think the sci-fi side of it, I mean, I don't, and then there's, the other big thing is just in medicine, there's so much happening right now in order to understand and really precisely be able to address certain mental states that you might be in. And so I think, I think sci-fi is not, there's a lot of things that are important to think about, and we should always be considering it. And in all of my students, this is always something that we're discussing in their dissertation and all the things how could this be, what are some of the broader impacts of it?
Yeah, thanks. That's
yeah,
that's great.
I mean,
it's reassuring that it's a constant conversation with your students.
Yeah, and I mean, and it's part of a bigger, I'm part of even a bigger thing where we have this NSF National Training Program at WPI where it's an NRT, where one of the big focuses on what does it mean that AI and robots and brain sensing and all of these things are coming and how that's changing it. And for that, all the students take a class really focusing on the implications of this, and then that leads into their dissertation. All of them who are funded by this have that in their section in their dissertation. But yeah.
Yeah.
So what are you concerned about?
That's great. Well,
no, sorry.
Sure. I mean, I'm concerned about, my brain being read. We have so much, challenge of moving information around. And so, emotional states are already manipulated. Mm-hmm. How much more effectively could we do that if you detect the mental state that someone is in? Is there a code of ethics that would prevent that? Is it just, or we just have to kind of hope that we have good?
So one thing is we're not detecting it without you, so you have to be wearing it in the first place. So there's already that. So this is people who decide that they want to. But no, I am concerned about that. One thing I'm finding is that there are people like me who are very concerned about it, and then there's a lot of people who aren't concerned about sharing, or people like to share, this made me really excited today, or this, and so there's some people who this isn't even that concerning. I think the manipulation of emotions is already happening without brain sensing, and I think there's a lot that can be done with or without it, but due to AI is even more being able to model and change things.
Yeah, in the team circumstance, this is research now, so I assume consent is here. But one question that arose is: are there conversations around consent to cognitive state monitoring in team situations?
Yeah, so actually that research project is about, we're kind of trying to see what could we detect, because then if we find out what we can detect, we want to know, how do people feel about that? Like, what if you knew that every time you work with this person you were stressed? Would that be useful to you? Now, what if that person knew that every time you work with them? Now, what if your manager knew that? And so we're actually using it more as a probe of like, what can we detect? And then how do we ask people, like, what is that? How does that change your feeling about this? And when would you see this as useful? Like, do you want your teammate, like, some people are like, oh, I wish that they could just read my mind. Like, sometimes when you work with someone who just doesn't get it. And so they have this, a lot of people we talk to, they say, oh yeah, I would love if like people could just understand what I'm trying to say and read my mind, or if I could understand what they were thinking so that I could change how I present something. But then we actually do it and see, okay, now like how does that actually, and that's the human-computer interaction part of it. It's not just like, can we do it, but like how does that change the dynamics, and what are people okay with and what are people not okay with? So that's part of the study.
And do you have any preliminary answers to that yet?
We'll see. We do have some preliminary, so because even before we did anything with the brain, we did a bunch of interviews of people, and so we have all of that data that were, basically people work on different types of teams, whether they're a leader of a team, whether they're just a team member, and from sports teams to like work teams, and just trying to understand what makes a good team and what makes them work well together. Because the idea with a lot of tools in technology is taking things that are, or people who do things really well in high performance and really think about something, and then sometimes we can build tools to make everyone do that. You know, just like, I don't know, ChatGPT has made it so that everyone can write better, whereas it used to only be people who had the skills to. And so, you know, there's some like, okay, proofread their work, but like, in an email. And so it's sort of like we're trying to see how could we take something that someone in a really high functioning team does and bring it to some of these lower functioning teams by being able to pick up on like, oh, this person like never says anything when they're getting frustrated. Like maybe we could like probe them to speak up or something, or just say that they didn't understand. Maybe we could detect that they didn't understand what that person was talking about, and they, you know, instead of just going home and not asking, like help them be more effective. But we don't know. We're looking at it because there's things people say that they want. They really think that this would be great when we interview them, but then when we try to actually put it on and see, that's what we're interested. Like, would you really want to see it, and who would you want to know this information?
Not to mention the cognitive overload of trying to process a whole new stream of information
right.
you haven't had to process before.
Yeah, and so I think that we're trying to, explore all of those. It's very early stages at the moment.
Excited to hear.
But it's really because now, for me, what I'm interested in is a lot of BCI work was always just putting a brain sensor on one person, but I'm interested in what happens when you have it on multiple people at the same time, and how that, I don't know, what's common and what's not common in that.
For sure. Another question that arose is, what about the computer communicating through ways that people might interpret facial expressions or things like that to convey information back to humans? Is that something people are experimenting with?
Yeah, so that some of the work that we're doing with like the embodied agent, for example, so I mean that's one aspect, or even if you use any of the voice agents, you're starting to see that they're becoming, like they're not just saying words, there's like emotion, and if it's an embodied agent, you might see them blinking their eyes, nodding their head, giving eye contact too, modeling what people do. So is that way?
Yeah, I mean, but cross-culturally, the signals are different.
Right, yes. And across the culture, I mean, so yes, and so that's another area that there's a lot of work. It's not so much what we're doing. I do work on cross-cultural design in a completely different area, but not with the brain sensing, but more looking, when I do work in accessibility, we're looking a lot at like differences in deaf culture, but it has nothing to do with this brain sensing, different topic.
Yeah.
But it is an important consideration, and I think that there's a lot of different levels of acceptance of computers doing things across cultures too, and different ways that people are quickly adopting certain things, and other places they're not adopting it.
So sometimes there might be processes that are helpful, mind wandering, right? Maybe that's associated with creativity, even if it does delay the speed short term. How do we take account of still evolving knowledge of the mind in developing interventions?
Yeah, I agree. I think mind wandering is really important, and that's why I think it's actually important to know when the difference between someone who's mind wandering versus like deeply like problem solving, and so being able to tell the difference is important if the computer is going to react to it. And I agree. I don't think we should prevent mind wandering, period. I think it's sort of context dependent, but just being able to identify when that's happening and help people if they need to come. Like some people mind wander and they sit down to work and they really want to work, but then they mind wander. And so they might be benefit if the system could help them, we detected this and you might need some support getting focused, maybe turn on some music or something like that. On the other hand, if you're just doing something creative or going for a walk, I think it's important to let your mind wander. I'm not saying that we should prevent it and everyone be efficient all the time. That's not the goal. But it's really, that's the understanding of the human, the task, the thing that they're trying to do, and their own motivation for using the system and designing all around that, not prescribing something like we should all just be robots. That's not the goal.
Could brain sensing AI help efficiency or safety for some tasks?
Yeah, I think we're already seeing it happen. We see that, we're able to detect places. For me, what was very eye-opening was when we did the study in driving, and I'm literally in the car with the person while they're driving and doing another task. And part of it is just sharing the information that actually, even though you think you are doing fine, you're actually not. And so giving people an awareness, whether it's because they're wearing a sensor or just because we've studied it and now it's out there that people know that your brain is affected by all the things you're doing at the same time and your performance might be degraded. And so again, it's not that everyone should wear brain sensors all the time. That's not my goal. It's really more to understand what's going on in the brain in the real world and then redesigning your life and your tasks around that.
Great. So if you could ask for input from this audience, artists, historians, mathematicians, physicists, social scientists, legal scholars, we've got a great audience, right?
I know.
What would you want to learn from their perspectives?
That's what I'm so excited to be here, honestly. I've been working on human-computer interaction for a long time, brain-computer interfaces for a while, and just watching this progression of AI and just seeing, what I didn't get at is, I was talking about how the interaction technique changes who can use something, and what I see now is ChatGPT basically made it so now everyone's using AI, whereas before it was us computer scientists, but we're using it to build a model or something, but now it's everyone's using it. And so it's really, we're just in this different place, I think, and I feel so lucky that I'm spending this year here with all of you, because I'd really like to talk about what it means, both how can artists use it and think about it, but also how do people study, even from historians, how they've studied certain things, study how do we probe what this means that we're changing the way we think and the way we do tasks and the way we interact with each other because of AI. And I think all of the different perspectives and legal perspectives, all of it matter right now. And it's important that we are having these interchanges, not just computer scientists doing things and then other people doing things somewhere else. I think the Radcliffe, that's one of the great things of being here. So I'm excited to talk to all of you.
Wow. Thank you, Erin, for your really interesting presentation and perspectives. I also want to thank our audience, both here and online, for the terrific questions. Thanks so much. And I hope everyone will be able to join us for other Radcliffe virtual programs. You can find out about future programs and watch videos of past events at radcliffe.harvard.edu. Thanks again for joining us today, and have a good rest of your day.